Hey all. We're going to, just like with the chain rule for last week and the first day of this week, we're going to break this up into two lessons. This first one you're going to do this week, and then you'll have the missing assignments homework, and then you'll do some more challenging versions of the same problem at the beginning of next week. I'm going to do just one video so that if you feel like you want to just watch the video, come back to it. You can also pause it, and I'll tell you where it's going to make sense to pause the video to do this first chunk of homework, and then we'll do the more challenging problem. So what we're going to talk about today is we're going to talk about what's called implicit differentiation. So get yourself ready for notes. And implicit differentiation is the way that we can do derivatives when we're talking about things that are not necessarily functions. So if I'm looking at something like a relationship is what it's called. So a relationship is any equation that relates two variables, usually x and y, but it's not necessarily a function. It might be a function, just like how rectangles are parallelograms, like they follow the same things, but a relationship can fail the vertical line test. So if I'm looking at this first equation, so this would be the example, x squared plus y squared equals 25, I would hope you remember from the last 2 years that this is a circle with radius 5 centered at the origin. Now obviously this is a relationship, not a function. It fails the vertical line test, but it can still have derivatives. It still has a tangent line, right? And remember, that's what a derivative is it measures the slope of this line at any of the given points. And if you look at a circle, it definitely has tangent lines. And they change their slope as it goes around. So it's going to have a derivative, but it's going to be a little bit trickier to figure out what that derivative is because you can't just follow the rules as easily. So the way that we are going to do that is we're going to use the chain rule. So what you have here is an overview of implicit differentiation. And the idea is, what do we do when we're going for dx, but the variable of the function is something else, right? You'll notice that these don't match. And remember, our goal is always dy dx, because that's our slope of the change in y over the change in x. That's how that's how slope works. So what you do is you take, okay, well I don't want, these two don't match, so I'm going to add a dy over dy multiplied together. That follows our rules of algebra. And then you'll notice I switched these two in the denominator, so now I have my dy dx that I want, and dy, which, these two do match. We are able to take that derivative. And so then you have f prime of y, because that's what that derivative is, but it's still being multiplied by dy dx. So what you're always going to end up is like, okay, take the derivative the way it is. Just take the derivative following any of the derivative rules that you want, but you have to end up multiplying it by y prime. And I'll show you what that looks like in a second. Usually the rule is that you do it later, so that's just like why we put radicals second when we're multiplying. It's just the general rule of how other people will show you to do it, so I'm just giving you that heads up. So again, what you want to do is, we've got d dx of both sides, just like we normally would. So here we've got x squared plus, and we're going to separate the terms right away, of y squared is equal to d dx of 25. Now, two of these terms work out just fine. This is one of our constant rules, this is a power rule. So you can already jump to, well, that's 2x, and that's 0, so that's totally fine. And here you'll notice, oh no, these two don't match. So I can take the derivative of y squared normally, but then I have to multiply it by y prime. I'll keep that addition sign. So multiply by y prime, and then you can just take d dy, where they do match, of y squared. And in this case, the derivative of y squared is going to be 2y. So we end up with the equation 2x plus y prime times y squared is equal to 0. And since we want to find dy dx, that just means that we need to solve for y prime, because that's equal to dy dx. Here we can just use some algebra. I'm going to bring it over here. So 2x plus y prime times 2y. Oh my goodness, where is my brain today? The derivative of y squared isn't y squared, it's 2y. I'm going to solve for y prime, so that means subtracting 2x on both sides, which gives me y prime times 2y is equal to negative 2x. Divide by 2y. I'm going to just simplify out the coefficients right away, so I end up with dy dx, or y prime, is equal to negative x over y. And so it's the only thing you have to account for is be like, oh, these two variables don't match. Take a y prime out, whatever this variable is, take that out, and then you can solve. So if this was z, this would become z prime, and then d dz of z squared. Whatever variable it is, you just got to take that out, and you'll get dy dx. Here's something I just want to review, looking at some of the check-ins and quizzes. Find the equation for the tangent line on the curve, because remember, that's what the derivative is. It's the slope of the tangent line. So y prime is equal to m. That's always true. And if we're writing the equation of a line given a point, I'm going to start with y minus y1 is equal to m times x minus x1. Now our x and y here are 3 and 4. So x minus 3, y minus 4. And then the slope is going to use this equation right here, negative x over y, so negative 3 over 4, because again, I'm just plugging in my x terms in those places, and then here's my y from the number. Now you can absolutely leave it in point slope form like this. If you want to distribute and solve, you can, but I would just leave it as y minus 4 is equal to negative 3/4 times x minus 3, and leave it in point slope form. Okay, if you want to pause here and start on the first day, you can. If you want to just keep going with the notes, finish those off, and have a lot of work time on your next assignment when you see this again on Monday, feel free. So pause here, or you can keep watching, and we're going to look at a much more challenging version. Here it says, find y prime if sine of x plus y is equal to y squared times cosine squared. So the way you want to start is just differentiate each side separately. So I'm going to start with sine of x plus y, and this is just going to be the chain rule, because we have our inside function here and our outside function. So the outside function is sine. The f prime then is cosine. The inside function g is x plus y. So this is the first place where we're doing our implicit differentiation here. So g prime is equal to 1 plus y prime times the derivative of y. And the derivative of y, when these two are matching, just like the derivative of x, is also 1. Using the power rule. So y prime times 1, or you can just write it as 1 plus y prime. So then the chain rule side is going to be the derivative of sine of x plus y. We're going to go with cosine of x plus y times 1 plus y prime. So that's one side using the chain rule. On the other side, we're going to be looking at, and I can just draw a line right down here. Here we have multiplication, so we're going to use the product rule. And this is why it's really nice to just have your notes out in front of you, have a notes and formula sheet ready to go, because then you're going to be able to jump right to this and not have to worry as much. So in this case, we have our f is y squared, and our g is cosine of x. Since we're finding dy dx, then we get g prime is straightforward. It's negative sine of x because the variables match. Here, it's going to be y prime times the derivative of y squared, which we've seen before. So f prime is equal to y squared times 2y. And I'm going to get an erase just to give myself a little space here. And now we can use the product rule where it's f prime g, so put my equal sign in there. So y prime times 2y times cosine of x plus fg prime, so y squared times negative sine of x. I'm just going to do a tiny bit of simplification, take that negative and make it into a subtraction. And so here we go. Now again, the goal is to find y prime. So we want to solve for this, but we have two terms. So if you remember in doing this in other lessons, what you want to do is combine those. So what I'm going to start with is distributing here, and I'm going to end up with cosine x plus y prime times cosine of x plus y. And that's just equal still to y prime times 2y cosine of x minus y squared sine x. Now to combine our like terms, I'm going to move them, the like terms, to the same side. So in this case, what I'm going to do is I'm going to add y squared sine of x to both sides, and I'm going to subtract y prime cosine of x plus y. And so that's going to bring this term over here, so our y primes are together, and then this will get over there, so our terms without y prime are together. Now I'm going to bring the work over here, which isn't the best organization, but I want to make space and not erase too many things. So we end up with cosine of x plus y plus y squared sine of x, so the non-y prime terms, equal to y prime 2y cosine of x minus y prime cosine of x plus y. And this is why you want them on the same side, so you want to factor out a y prime, because then you're just going to divide by that factor. So in this case, you get y prime times 2y cosine of x minus cosine x plus y. And then we're going to divide both sides by that. So cosine x plus y squared sine x. And we end up with a very large rational expression, but that's just fine with the numerator. And then we divide both sides by 2y cosine x minus cosine of x plus y, y prime. So there you go. It's much, this is obviously a much more complicated example than our first ones, but I wanted you a chance to see both and get 2 days to really work through them. If you have questions, please let me know, and I'll be available on Zoom, by email, or in the comments.